Today on Diode, the continuation, video number 4 of the repair of 6 show lasers. So there are 2 Citadines left that have some minor problems. This one has problems with the green modulation and the other one has problems with the galvos. And that one might require parts to be ordered up. So on this one, what I want to do right now is check the green laser to see if it's outputting at least at threshold. Now what does that mean? Inside of a DPSS laser, there are secondary optics and crystals that take a little bit of time to reach saturation until they laze properly. This can either be LBO, which stands for lithium triborate, or BIBO, which is bismuth triborate. It does not operate like a green laser pointer does, where it has the KTP and the YBO4, the yttrium orthovanadate and potassium titanyl phosphate. More about that on other videos. So right now what I'll be doing is I'll be turning on the laser. I won't be putting a signal in, but I'll be using one of my modified camera phones to take a look and see if I'm getting any infrared light through the aperture in the front and seeing if there's any activity inside of the laser chamber itself. For that, I'll be using one of the modified Samsung Galaxies, of which I took off the IR filter in the front. So that'll give us a little bit better of a view in that, and I'll switch over to that video when I do that. So first step is to turn on the laser and situate the interlock. So let's do that. It's key time. And we'll get a beam stopper. Put that there. Save the eyeballs. No accidents happening with the eyeballs. I lose my job if I can't see what I'm doing. Laser safety. Laser safety. Alright, well, the laser is turned on. I'm going to move over to the other camera and I'm going to turn off the shop lighting. We can take a good look at the pump diode laser head. This is what I'm going to be doing. I'm going to be using this camera to just peer inside of the laser like this. Take a good look at what's going on. Alright, now using that modified camera phone, we can take a look at that laser head. Do not attempt to adjust your TV set. Everything is A-OK. Let's take a look at the aperture, and we can see that the pump diode appears to be reaching threshold. A little bit of digital zoom will give us a slightly better image of what's going on. It looks like it could be a C-mount laser dial, and definitely looks like to be a resonant cavity style laser, and not one that's based on a monolithic crystalline assembly. So yes, it looks like that the laser head and driver seem to be working just fine, and aren't getting modulation signal at all. Interesting. Later on we'll pop open one of these laser heads and see exactly what's inside. Okay, I've taken it off the back of the cover so that way I can get inside and figure out what the green problem is a little bit more, have access to all those wires. Before I get into that, let me finish up what threshold means. Inside of the green laser, the crystals that turn the infrared to green take a little bit of time to reach saturation. So what they do is they put in just enough infrared light to the point where those other crystals are barely lasing. So that way when just a little bit more power comes in, the laser crystals can come on quicker and faster. And you don't normally see the infrared light at all, and there's very, very little coming out of that green laser. I mean, a very minimal amount, so good job with the IR filtering on that. Let's get you testing out the signal for the green laser. This is the green laser driver right here, and I'll be pulling out the analog feed signal. I'm going to reach in, grab that. Yep. Pull that out. Here you go. So this is a cable that sends the analog signal from the laser driver to, from the scan card to the laser driver. So my output signal is from 0 to 5 volts. Going to be coming out of here. So I'm going to be using a little blue LED to test that. So what I'm going to be doing, since I don't want to burn out the LEDs, I'm going to be setting the brightness on the program to lock in at about 40%. That way I'm not overpowering the LED with 5 volts. And I'm going to turn on the laser, and we're going to diagnose that line. On. Now we wait for that relay to kick over, and we'll see what the LED tells us. Waiting. Waiting is my favorite part. Love it. It's like being at the DMV. Here we go. Okay, so now the laser is on and active. We have output to the other colors, yes. Oh yeah, that's right, I have a beam block. Haha, safety. Alright, so let's test the green, see if we're getting anything out of the green real quick. It looks like we are. So, I'm going to bring up the brightness on that, and the brightness should go up, which it does, and it should go down. So it looks like that the laser driver itself is actually getting a signal. That means there's a fault somewhere in the laser driver. Oh boy, that sounds fun. Take a look at that. Okay, let's look over the board. So the board basically comes in two parts. One part for controlling the TEC, Peltier junction between the laser head and the heatsink, and the laser driver itself. So, since we're having problems with modulation, let's take a look at the modulation side of the circuits. We have our input here, and we have a couple of op amps here, and those are tuned with these potentiometers down here. We have this MOSFET, and this MOSFET is not part of the laser driver circuit. This MOSFET right here is. And we have all of these components here, so we have a couple of smoothing capacitors, looks to be a resistor shunt, and a TPS diode. That's a transverse voltage protection spike stuff. And we have this side here, which is output indicator, the resistor network, and it looks to be another operational amplifier. The majority of these components here are for regulating the thermoelectric junction, and that right there is actually the setting resistor. We have a bicolor LED that either turns green or red, and this is connected to the quad N-channel MOSFET full bridge driver. So we have two N-channel MOSFETs right here, and we have another pair of two N-channel MOSFETs here, and we have the little drive network for running those, and then the inverting transistor totem for that. So yeah, looks like all the resistors are good, all the potentiometers are good. So let's flip her on, start testing some voltages. Okay, with the unit powered up, we can start testing our voltage rails. See what the green laser, oh, it's on. Interesting. So we do have green laser. Alright, I tested that earlier. We're getting 5 volts on the output and nothing. I'm betting you it's at our golden number now. Let's see. Our golden number should be around 2.35 in volts. Take a look at that. .23 at half. Yep. Okay, we're around that number. Okay, so what's the problem? It's not a problem on the laser driver, it looks like. Check the cables in the back. Maybe it's the cable going into the laser head. Move the camera, we can diagnose that. Okay, so with the laser now on, I'm going to jiggle that cable that's going up to the laser head and see what happens. See if it cuts out at all. Yep, that does seem to be the problem. So let's pull open the laser head and see if we can check that out. We're starting this earlier than expected. Time to get into the green laser head now. So I'm going to be undoing the outside case screws. Or not. Those are quite hard screws. Give me my tool. Gotcha. So it was asked how these lasers get in such a bad condition. Well, while I'm undoing this, let's explain that. See, in traveling, they'll get knocked around, a vibration will get to them, and also many times they'll be set on things like speakers or other things that are vibrating quite a bit due to the sound system and such. So, vibration is a real killer of these things. That's the biggest thing. Plus, as you notice in some of them, the fog juice can get into the components, start to cause damage, poor construction, dust, overuse. And we're going to get into some of the other problems with the galvos in the next laser. See if those are fixable or not. I'm hoping this gives me good access to the wires inside of the laser head. I'm really thinking that one of the internal wires got pressed in due to the pressure from the back of the case, and that's where our faulty connection is going to end up being. So let's open this up, and there's not really much going on the inside of these guys. Just a FAC lens. I see 2 more screws up here. Thought you could get me, but you didn't. Anyway, not too much going to be happening. Not too much is going to be happening inside of this laser head here. It says it's going to be the pump diode, or 2, FAC lens, and then maybe 1 other lens for focusing, and then the resonant chamber in the front here, under about where this label is. I don't think there's going to be any thermoelectric junctions, though. Didn't see any wiring for that. Well, let's see what's inside. I think she's ready to come off. Should be fairly straightforward, just 2 connections. Yep, fairly straightforward, 2 connections. Okay, let's take a look at inside of the laser head itself. Looks like we might have right here a custom 23 watt IR pump diode, an 808 pump diode. You can see like the electrical connections coming in here, and then it looks like the case connections coming in through here. So it's probably one side of the connection. Interesting assembly. On the front, it doesn't look like there is a FAC lens, but it does look like there's a prism of some sort, which would explain why the light coming out is off at an angle and coming into it this way. So let's take a look at the resonant cavity. So here's a resonant laser assembly. See, we got 3 parts here. We've got this little mirror and that mirror, this little lens assembly here, and this little lens assembly here, and inside of this we have a resonant crystal, which is going to be the lithium triborate or the bismuth triborate. Now that crystal inside of there is actually susceptible to atmospheric moisture. It's deliquescent, which means just like table salt, it likes to soak up the moisture in the air, and that can be very damaging to the crystals. At the end we have a beam steering prism. So the light that is coming out from the resonant cavity right here is going to be moving this way, and then when it hits that prism, it will be moved into the forward position. So pretty simple laser head. As I said, no thermoelectric cooling on here at all, and I don't see any thermoelectric cooling on here. Absolutely no feedback compensation whatsoever. So very disappointed with the inside of this laser head. Not much to see. Well, I've got the laser head working a little bit, and I've got the cover taken off. I'm going to do something extremely dangerous. I'm going to show you how much IR is coming off of one of these lasers, and the comparison between a regular camera that sees how you see and one that's capable of seeing the IR. Let's do that. I'm going to be looking away from this. Do not do this. This is extremely hazardous. So I'm going to take out the cover ever so slightly. going to turn off the light. And I'm going to turn off the laser to its output brightness. And I'm going to turn off the light. And I'm going to turn off the laser to its output brightness. So you can see that there's a lot of infrared light coming out of that laser head. That is not joking around, and that is dangerous. And even there, that's a lot of infrared. And even there, that's a lot of infrared with the laser, even just in the threshold stage. In order to get access to the wires in the laser head, I'm going to remove the laser head. It's 4 screws, and then this will lift up, and we'll see the thermoelectric junctions underneath the laser. So yeah, let's do that. I think that the block behind here has 2 screws coming up from the bottom, which is most likely the case. So removing the laser head is necessary at this point. After I fix the wires on this laser head, I think I'm going to pull out another one of mine and show you the inside of that and how I came to the conclusion where the problem in this laser head is. As I said, I made the comment of looking for the golden voltage, that right voltage range, and that 5 volts was the wrong one. I will get into that a little bit. It's a lot easier to explain with the stuff in front of you. No, there's going to be a whole lot of heat sink thermal compound in here. I think so. Oh yeah, clear indicator. It's going to be messy. Alright, I believe that's all 4 screws. Carefully lift this up now. Not quite. There we go. Oh yeah, there it is. And it looks like we have what looks to be an acetal spacer. What to note those. Looks like there's 4 little washes between there as well. Okay, makes sense. Yummy. No screws on the bottom. Huh. I see, screws on the back. Well, you know, we're here now. Let's get that pressed down into position. Yeah, there's some clear fluid in here as well. Probably a sealer. It looks like the silicon oxide, that crap thermal compound. One screw is missing. Interesting. Let's pull that screw off as well. And I'll remove that. Yuck. Yeah, that screw is gone. Wonder where that went. Oh, wow, that screw's way loose. Oh, I wonder if somebody's been in here before. Interesting. Oh, this is way loose too. Okay. Boy. Ah, tight screw. There's one tight screw. I don't want to lose that little washer. Alright, then to undo those ones on the top again. Fair enough. Oh, I tightened them. And those ones are a little shorter than the back screws. Okay. I'll make note of that. Well, that should come off. Yes. There's still quite a lot of force from the cover. Loosen up that cover a little bit. That'll work with that. There we go. Let's see how our connections in the back look. Oh yeah, so here we go. Swoop around. So we have here either with a reverse protection diode or a Zener diode. Zener. And check this wire out. This wire is loosey-goosey compared to that one. So I'm betting there it is. Well, alright. That's the problem. So let's go ahead and fix that. Resolder that wire back onto the laser head. Put that down. Get the clippers. Alright, let's start by clipping the heat shrink that is there off the wire. Try not to clip the wire. Alrighty. See if we can get some new heat shrink on the wire. Too much. It's a soldering time. Now, when doing any kind of soldering on a laser device, do have it unplugged, so that way you don't risk anything getting through the device and possibly damaging that laser diode. Alright. Ah, the fun stuff. We squeeze that down with a pliers. Something. I have buried my pliers. Success to the archaeologist in me. And try to give that a little bend at the end there too. Oh yeah. Yeah. Very nice. Very nice, very nice. Oh, you can do it. Come on. Yay! Now we'll heat shrink that into place. Well, the quickest way would be using the soldering iron. Yeah. That'll work. Get a lighter or something. Alright, I'm going to heat shrink that in place. We're going to get that cover back on. Got the laser head back in. All cleaned up on the top. Looks all ready to go. So let's go ahead and check it out. Give it some power. Turn on the interlock. See if any smoke happens. Got our beam stopper right here. That way you don't lose our peepers. And now we wait. Come on, relay. There we go. Alright, let's see if our green is working. And it is. Very good. Galvos sound a little rough. I can hear them, they're quite loud. Let's get a full colored hue going. A lot quieter. Carefully remove that beam block. Shut her down. And let's see what we're getting. Oh yeah. Last another laser down. Let's get on to some more laser stuff. As an introduction to understanding the golden voltage number, let's talk about current and voltage regulation and the difference between them, and the difference between positive temperature coefficient and negative temperature coefficient. So, if we have here on this end of the laser driver, we have a metal oxide resistor, just like a wire or a tungsten filament bulb. Any other resistive component pretty much will get more resistive as they heat up, which means they'll lose conductivity. A lot of semiconductors, LEDs, and laser diodes share the other end of that spectrum, so to speak, where they have a negative temperature coefficient. That means that the warmer they get, the more conductive they get. Here I have a power supply which is capable of both current and voltage regulating. So I'm going to turn up the current all the way to its set point, and I have about 3 volts running through here. I have a heat sink on these LEDs. So you'll notice right now, while we're regulating in voltage mode, that the LEDs are taking about 1.3 amps at 2.8 volts. They're on the heat sink right now. The only difference I'm going to do is I'm going to remove the heat sink. When I remove the heat sink, you're going to see the current start to climb as the LED array warms up. So I'll remove them from the heat sink now. So now the heat sink is off. And it might take some time to warm up the LEDs at this voltage. We'll hold this here for a while and see what the current climbs up to during the operation. So right now we're up to about 1.8 amps, which is a bit more power than it was drawing when it was cool. The voltage has also changed a little bit, but not much. So all that extra energy now is going into the junction. The junction is getting warm, it's drawing more power. So the laser diode in this case would do the same thing, which is continue to warm up, continue to take more power, and eventually you would wear out that junction. Let's go put the heatsink back on. You'll see those numbers start to climb right back down pretty rapidly. So let's talk about current regulation. Say we wanted to hold our set point to 1.3 amps and not have any more going through the circuit. Well, we can do that. So we're going to use the current knob to control the amount of amperage, and we're going to look for that voltage, look for that voltage drop and the current drop. So let's turn up the voltage a little bit more, and now we're in current regulating mode. So I can turn the voltage up now, and you'll see that here we have significantly more voltage, but the current is regulated now. So I'm going to remove the heat sink, and we're going to see what happens to the current during this. So now you see that everything is running in current regulation. The LED array is still rather cool. Nothing is going out of control. But what voltage are we actually running through the system now? It says 2.8 volts. Let's disconnect the LEDs. You see how the voltage shot all the way up to 17 volts? Yet if I reconnect the LEDs, they're just fine. They don't blow out at all, but we get a drop of voltage. So when I saw 5 volts, I knew that that voltage was too high, and it indicated that there was a open in the system. Let's get into explaining the other DPSS laser heads. Now that you have seen how current versus voltage regulation behaves in power supplies, let's take a look at how the lasers operate. All of the DPSS lasers that work in most of the show lasers operate with a aluminum gallium arsenide laser diode, which is the 808 nanometer frequency pump diode. The electrical voltage that is applied across the junction is determined by the crystalline structure chemistry. So all of the 808 nanometer laser diodes, because they have roughly the same chemistry, will have the same voltage across the junction, which is anywhere from 2 volts to 2.35 volts, depending on the output power, maybe 2.4 volts. So let's take a look at how the meter responds to those. We have the meter here. This is a 30 milliwatt, probably has about 200 milliwatt 808 nanometer pump diode in it. Plug it in. And we'll see what the voltage is across the gate as it's running, or across the junction. So we've got a reading here across the laser diode junction. It'll be backwards. So 2 volts. Fair enough. Let's unplug it. And we'll run the laser driver without the laser diode in it. Let's check the voltage again. Now we're getting 3.1 volts. So you can see where the voltage is higher. Let's go ahead and test out a higher powered laser device. Okay. Here's a 150 milliwatt output laser. So you can check the voltage across that laser diode junction as well. And we should get roughly the same voltage. Let's go and test it. Where are ya wires? There we go. So once again, about 2 volts. So as you would suspect, the higher the output power on the pump diode, the more current they require to operate. Let's unplug that laser, disconnect the laser head, plug the power back in, and we'll test that output again and expect the higher voltage to appear. So that's 5 volts right there. Let's go ahead and check out a larger laser head. Finally, let's test another DPSS laser head. This one happens to be another resonant style and not a monolithic crystalline style. So let's test the voltages. This used to be a 500 milliwatt output laser, but only puts out about 300 milliwatts at this time, just because of alignment and crystal degradation. Let's check the output voltage on there. So we're getting the 2.3 volt range, so right again, really close to that 2 volt range, which is to be expected. Now, once again, if I take off the power, and we'll test the voltage coming out of there, we're going to get a higher voltage. Now, considering that the power supply that was feeding that laser driver was 5 volts, and we were getting the full 5 volts out of the power supply, or at least I was in the initial testing, I had suspected that there was a break in the line, just due to this. Here we go, testing again, 3.7, so not quite as high, but the higher voltage is still present. So, that was my thinking, and that's what it turned out to be. Now, this is a good way to double check to see if the cables inside of the laser head are making proper connection to any of the laser drivers. If you see any voltage above 2.4 volts, you know that there's a break somewhere. If you see a lower voltage and you're supposed to be getting full power that's lower than 1.8 volts to 1.9 volts, you probably have some problem with either the pump diode being burned out or insufficient power getting from the laser driver, either from a bad power supply or bad caps or a blown out final transistor. So let's get on with the laser galvos and the other steady laser. I pulled the 2 galvos out, and now we can start using the meter to see what the differences might be between the two to diagnose them. First of all, let's check the coil continuity between the two of them. The coil continuity on a galvanometer is usually anywhere from 3 ohms to 6 ohms. So let's check that out. The coils are easy to find. So if you take a look at here, let's see, in the back, we got those two. Those two lead up to these 2 pins right here, which if you look on the other side, are where the little coils connect up to. See a little bit more on that side. So let's check the resistance on those pins and see what they say. Oh, wrong pins. 3.8. Cool, that's good. Okay, so you'll notice that this galvanometer has 7 pins. Some galvanometers have less or more. Usually there's 2 for the coils. There is a common ground, there's one for the IR LED, and then there's one for each of the tilt sensors inside. So let's see if we can find a common ground on here. I'm betting there's one. So usually the common ground is the 2 pins here on a 7 pin. Those look to be good. See if these are good as well. Yep, those seem fine. Okay. Yeah. The next 2 pins are for the IR LED. So when you find the common ground or your ground at all, you're going to be testing the LED. So let's check that. Let's check on the other one. .8 mega ohm. Yeah, I knew that was a little funny. Okay, and then from the common ground over to the 2 sensors. Yep, those are open. That's good. 1.8. 1.9. That seems fine. Looks like we might have a bad IR LED in this one. Interesting. Let's go over to diode mode and see what the meter tells us on this one. So, common ground and the LED. Okay. Common ground, IR LED. Nothing. Flip it around. Absolutely nothing. Yeah. Right. I think I'm going to swap the IR LED in the back. So, let me show you what the IR LED is in the galvanometer. And as I said, there's a little bit more about how these work on another video. Yeah. There's the little IR LED right here. And I'm betting that that's bad. We can test the, well, I can test the IR LED using a modified phone. So, I'm going to open up the other one too. Actually, you know what? I'm not going to open up the other one because I know that works. So, using diode mode, which puts out a little bit of power, we can actually send power to the LED, and we'd be doing that by putting the ground on the common ground, or the negative on the common ground, which are these connections, and then over to the LED. So you get nothing. So turn off the light, turn on the modified camera phone real quick. Make connection, see if we get any visible output. Yeah, I killed the patient. Alright. Yeah, no activity at all from that LED. But it's dead. Let's replace it. See what we get. On to more laser surgery. So, I'm gonna see if I can carefully extract that IR LED. That's glued in rather nice. Man, not making my job easy today. There you go. A brutal extract indeed. Alright. So, we have the anode and cathode. So, cathode on that side, anode on that one. Groovy. Get that cleaned up a little bit. Cool. Time for a donor. So I think I'm going to pull that LED out. That should work just fine. Solder. So I'm going to bend the little LED legs up like this. Then I'm going to solder it down onto the inside of the galvanometer. Let's get some solder into those areas. Excellent. Plastic fumes. Delicious. Not too bad. Let's go ahead and check that on the meter. Looks good. I want to move the LED a little bit more to the other side, but I think that's going to make a lot of difference. Right, let's put the cover back on. There's a hole there. Right, I think we're good. Yep, looks good. Time to test. So, got the X Galvo connected up to the X Galvo amp. Hopefully it'll do something. So, there's one area, there's the other. I'm hoping that it'll meet somewhere in the middle at that angle. So, let's see what it does. Turn it on, and hopefully that made some progress. On. Power. And scan safety doodad. Oh, I hate the waiting. Nope, that Galvo is done. Time to do a few more tests to make sure that the problem is only in the Galvos and not the two Galvo amps. So I'm going to take one of the other Galvo kits and I'm going to plug it into the Galvo amps and turn on the laser. See what happens. These Galvos behave correctly. Then I have a good suspicion that we just have bad Galvos. Alright. On. Safety. Now we wait again. That's interesting. That one works. Huh. I'm starting to suspect. Oh, nope. Now they're both locked in. Okay, yeah. The amps seem like they're working just fine. Okay. Yep. Bad Galvos. let's do another little test. For this next test, I use a big powerful magnet, and I'll pull it out. And you really can't use a small magnet for this, just because it really doesn't have the kind of power required to do this. So, get the big magnet out. This is the kind of magnet that scares your debit card and hard drive. So, pretty big magnet in there. We're going to keep it in there just as is. That's all we need. So, let's take a look at a couple of galvos. So, got one galvo here. And let's make sure we can get some focus on it. And with a magnet, you can see that I can make the galvo mirror deflect. Pick up another one. And here we'll be paying attention to the back of that tilt plate. There we go. I can get that to deflect pretty easy. Now, go to the other galvo. Just this one out. So you get any movement at all. And it's dead. So that's how you can check for a weak magnet inside of a galvanometer as well, using a pretty big magnet. So it looks like that the magnets in here, either due to overheating via just moving back and forth too much for too long of a time, the wider you scan, the less effective the magnetic field is against the coils. So the more effective scans are the tighter ones, and the least effective ones not only take more power, but are also least efficient to do. So they produce a lot of heat in these galvanometers. So it seems like that's what the problem is. Bad magnets. The amps work fine. That's where we are. There's nothing you really can do about those magnets. Once they go bad, they go bad. It's kind of the nature of things. Well, I think that pretty much covers everything I want to do for this video. I've got one more laser working, which is really good. The next video is going to be installing new parts, so new fuse holders, the new ILDA port, could be a couple of new galvo kits as well, and it's just pretty much general hardware. This laser right here looks to need new galvos. The amps seem to work just fine. So that's where I'm at with this one. That'll be in one of the new parts installation videos, probably the next video coming up. And then the last video will be installing the new red laser diodes in the other light space unit with the new galvanometers if they come in. And then from there, the miscellaneous aligning of all the optics in the lasers. I'm also looking for more questions to answer, so if you have questions, let me know. Leave them in the comments, and I'll try to address them in the next video as best as I can. As well as the final video, I'm still thinking about doing just a rundown and history of how I got into lighting, from being very young and having broken flashlights to now servicing some of the coolest lasers I've ever seen. I mean, God, it's fun. Well, as always, stay tuned for more.